Hello, my name is Rom, so I'll be the tutor for today. So today I'll be explaining some basic mathematical probability concepts and involving some basic terms in statistics and probability. And some of the terms that we will cover today will include like sample space and what is probability, and moreover, we will dive deeper into two special events in today's content, and mainly they will be about a mutually exclusive event as well as independent events. So let's start. So at the start of our lessons, I will introduce some basic terminologies that we must make sense before we can do some actual probabilities. Okay. So the first concept I want you guys to know is the sample space. Um, okay. So sample space is a set, okay? So what's this set about? The set is a set that's going to include all the possible outcomes. So for example, if when we are tossing a die, right, and we want to know that which number is going to face upwards. And from experience, we know that there's going to be a number that's ranging either start going to be 1, 2, 3, 4, 5, or 6, right? And putting those six numbers in a set notation and in that way we will have include all the possible outcomes, right? And then we call this set a sample space. And another example of sample space might be tossing a coin. In that case, we might get a head and a tail, and putting that into a set, we are going to get a sample space. And one thing to notice about sample space is that we often tend to use the Greek letter omega to denote the sample space. Okay. And secondly, I'm going to define what an event is. So event is basically just a subset of our sample space. So it can be any subset, or you can like, for example, it can be an empty set, or just be the full set of the sample space. So in either way, it's going to be so any subset of the sample space will be an event. For example, when we are tossing a die, we might be interested in outcomes that's an even number, right? And those numbers will definitely include like 2, 4, 6, right? And we know that the set of 2, 4, 6 is actually a subset, right? It's a subset of the sample space, which is the set that contains all the numbers from 1 to 9, 1 to 6, sorry, right? So knowing that this is a subset, so we know that we can define this as an event, which is going to be the event that we are going to toss an even number in one toss, right? And certainly we're going to study the concept of union and intersection. So when we have like two events or two sets in either way, so when we want to know about the union, as you can see, there's like a letter U, which is not exactly the letter U, but it looks like the U. Okay, so the union between A or B, or we call the A union B, is a set which going to include all the outcomes from both set A and both set B. So the emphasis here is on the or. So what we mean by this is that it does not have to satisfy both. As long as as long as you have an element which either come from A or come from B, you can put it into this union. Okay? So maybe we can use an example to illustrate this. So, okay, suppose for the set A, we have numbers like 1 and 3 and 5, right? And then for number B, we might have number like 4, 5, and 6. Okay, so maybe we want to know about the unions. Okay, so union means is as long as it's one of the numbers in one of those sets, we can put it into it. Okay, so for example, like for this one, you know, 1 is in A, even though it's not in B. So as long as it is in one of those, we can put it into the union. Okay, so we have 1. And then we have 3, right? 3 is in A, not necessary in B, so we can put it in. And then afterwards, we have 4, which is in B, even though not in A. And then we have 5, okay? But we notice phi is in both A and B. But given that this is a set, we don't repeat elements. So we're just going to put one phi into the union. Okay. And then afterwards, we had this six in B, even though it's not in A. But anyway, we still put it into the union because as long as it's in one of those, we can put it into the union. Union, right? Okay. And secondly, what we want to know about is going to be intersection. So as another way to rate the intersections is we can rate it as like A and B. Okay. So as you can see, it's like a downward curve. It's like a downward parabola, uh, like for the symbol. Um, although it's like not like the letter N, right? But it's kind of similar in terms of like the shape for the symbols. Okay. So for the intersections, what we want to emphasize here is that it must the set that the set of A and B must be all the elements that in both A and B. Okay. So in other words, you can't put numbers that's only in one of A or B. It must in both sets. All right. So using the previous example that we just gave. So one thing we notice is that only phi is a number that's in both A and B, right? So in that case, our intersections will simply be phi, all right? Because that's the only number that appears in both A and B, and that's what we call the intersections. So so the emphasis here is that both sets they have to be satisfied. Okay. Okay. After exploring some basic terminology, we will now dive into actual probabilities. So the first probability that we want to look at today, like assuming that you guys already have some basic probability concepts. So the first thing we want to explore today will be the joint probability. Okay. So joint probability, which is the same as like two events happening at the same time, right? And then we know from set notations, when you have two events happening at the same time, it means it has to be intersections, right? Because you have to satisfy like both events, right? So the notation to denote the joint probability would just be probability of A and B. All right. And this is what we call the joint probability. It has to be the probability of event A and event B occurring at the same time. And because they have to satisfy both sets, so that's why we are putting it in the intersection or little n in the middle between A and B. All right. And afterwards, we are going to find a way to explore find a formula to explore the relationship between between the individual probability like the PA and PB as well as the probability that A or B happening. Okay. So the formula is given as below. So we can see the probability of A or B occurring is going to be the sum of the probability of A plus the probability of B and minus their intersection probability. And in a 1 second, we're just going to explore how this formula is going to be derived. All right. So one way that we can demonstrate how this formula is derived is that we can use a notation called the Venn diagram. Okay. Suppose we use the left circle to represent the set of outcomes in A, and we use the right circle to represent the outcomes that are in B, okay? And as you can see, the the intersection part is going to be where A and B overlap each other, right? And then one thing here, so the property of A, which is going to be this part, right? So we are only looking at the circle that's inside A. So that's going to be our PA, okay? If we look at the probability of PB, again, we are using the same diagram for illustration purpose. So we can see that for probability of B, we are just only going to locate the circle that's inside the circle B, right? And we're going to use it to denote probability of B, okay? And here, okay, and then for of course for the intersection part, um, is clearly going to be the overlapping bit, right? This is what when we have like two events occurring at the same time, and which is like the intersection. A intercept B, right? And that A is probably occurring. All right. And finally, mm, um, the thing is, what we want to get at the end is clearly going to be the union, right? Okay. So what's going to be the union? It's going to be because as long as we satisfy one of those, we are good, right? So it's going to be this bit. Okay, so that is going to represent the probability of A or B occurring, right? And given the formula shown below, we have the probability of A or B occurring is going to be the probability of A plus P probability of B and then minus the intersection probability. And then we want to see why is that this case. So as you can see, if I add this circle to this circle, how many times is the intersection bit being counted? It's counted twice, right? So, but in our A or B, how many times we want to count the intersection part? It's only once, right? Right. So to avoid the intersections being counted twice, we had to subtract the intersection bit for once, so that only the intersection bit is counted once. Okay, so this is pretty much how this formula is derived. All right, and the next thing is that we probably want to locate example. So suppose that A is the event where we toss a coin and get a number greater than 3. And from past experience, we know that it's going to be 4, 5, 6, right? That only these three numbers are greater than 3 in a coin toss. Okay. And we can now suppose that B is an event where you toss a coin and get even number. So out of those, we know that that's going to be 2, 4, 6, right? And to calculate the probability of A or B occurring, okay, that's the end. So we want to calculate the probability of all, okay? So to calculate this, using the formula, we know that it's going to be PA plus PB minus the intersection probability, right? All right. So, but before we do this, we might want to know what's going to be the intersections, right? So for these two sets, what's the number that appears in both A and B? There's going to be 4 and 6, right? So let's start from PA, okay? So in A, we have three numbers. And then in our sample space, which is going to be the set of all outcomes, we have six numbers. So what's the probability of getting an A? That's going to be 6, 3 out of 6, right? And for PB, for which you have the three numbers, so that's also going to be 3 out of 6. And how many numbers are in the intersections? Only two, right? So what's the probability of the intersections? It's going to be 2 out of 6, right? So what's the final result? We have a half plus and half, and then minus a third, which gives us 2/3. Okay, so that's how we calculate the union probabilities. Okay, and after exploring the relationship between joint probability as well as like the over probabilities, and now we want to explore something slightly harder but quite useful later on. So this probability that we want to explore is called the conditional probability. And the notation is given out is like this. So the first thing we want to know is that how do we rate this notation? Okay. So this notation is you can see a P, an A, and a bar and a B, right? So the way to read the bar is that you read it as given. So this notation just means what's the probability of A occurring given I already know B occurs. Okay, so it's like a little bonus that you know beforehand, before we want to predict whether A occurs or not, right? So the B information being presented to us is that we already know B occurs. And you want to use this information to update or get a new estimate for your for your probability of A occurring, right? And the conditional probability is calculated as follows. Is that we use the intersection probability, which is going to be the joint probability between A and B, and then divide by probability of B. And then you might be interested to know, like, how is this obtained? Okay. So again, we're going to use a Venn diagram to illustrate this. Okay. Suppose we have the left circle representing A and the right circle representing B. Okay. So what's been given to us? We already know that B occurs, right? So if B occurs, my results we're going to lock in into the circle B, right? Because I already know B occurs, my results cannot escape outside of this circle, right? Or outside of the B set B. All right. And then I want to know that given that I'm already inside this B circle, and then I want to find out whether my A occurs, right? And then inside this red circle, what's the bit that we also have A occurs? That's going to be the intersections, right? So it's like finding A inside B. And then the only way we can do that is through the intersections, right? So it's like finding the intersections inside B, right? So this is why we want to use like the blue area to divide by the red area, like to get like how much out of B is we also how much out of B we also satisfy A, right? So this is why we want to use the blue bit to divide by the red bit, right, to get a probability. And then for the blue bit, we know it's going to be intersection. And for the red bit, it's going to be the probability of B, right? This is how the formula is derived. Okay? And I hope this makes much more sense now. And if you later on we might use an example to illustrate this. Okay. And then after exploring conditional probability, the next thing we want to dive into is our two special events. And they are mutually exclusive event and independent event. Okay. So we might want to know that what is a mutually exclusive event. So first thing, there are two events involved. Okay. We can call it A and B. Okay. So when you have like a mutually exclusive event, it means that these two events they cannot occur at the same time. Okay, in other words, they're intersections, which we're going to be the empty set. For example, if we can have A to represent the event where you toss a coin and get an odd number. And we can have B to represent the set where you toss a die and get an even number. And we know that a number cannot be odd and even at the same time, right? So this is an example where we have two mutually exclusive events where two events cannot occur at the same time. So this means that if I already know that A occurs, I can pretty much predict that B cannot occur. And then I can also do it the other way, right? So if I know B occurs, then I know that A cannot occur, right? So that's how we define mutually exclusive events. Okay? And then the next thing we want to study will be the independent events. So what independent events is means that the occurrence of event A will not affect the how likely uh, will be occurs. And this is also satisfying the other way around, which means that if I know that B occurs, this will have no helps in terms of like predicting whether A occurs or not. So it's like the information of A occurring doesn't help me with predicting B, and knowing B occurs or B does not occurs also doesn't help me predict whether A occurs or not, right? So in this means that if I know A occurs, this is not useful for helping me knowing B occurs or not. And this is true the other way around, right? So it's pretty much like two events that it's like you are going to either get is that is that, for example, we can define A to be the event that you're going to get KFC tomorrow, right? And we can define B to be the probability that you will rank on the first of on the first of January next year, right? You can clearly see that these two events are independent, right? Because even if that you are going to eat KFC or not today or tomorrow, it's not going to affect whether it is going to be rain the first day of next year, right? So so that's how we define independent events. So the next key question we want to ask is that, which is a question that often students confused about, is that we want to know that is mutually events independent events? Okay, okay, and then the answer to this question will be no, right? And we might ask why. Okay, and the student often confused because they thought that those two events are the same thing, but it's not. So we might want to know why is this the case? So for the independent events, we know that knowing A occurs should not help you predicting whether A, B occurs or not. And it's true the other way around. It's like if I know B occurs, it should not help me predict whether A occurs or not. And that's how we define independent events. But coming back to mutually exclusive events, we know that if A occurs, if I know A occurs and the A and B are mutually exclusive event, and I know straight away that B cannot occur, right? Because I already know that A occurs. And similarly, if I know B occurs, then I know straight away that A cannot occur, right? So this is pretty much saying that if I know whether A occurs or not, and then I know whether B will occur straight or not. So, and then by knowing whether A occurs or not, and I know about B straight away, right? So pretty much like so in mutually exclusive event, the fact that A already occurring already gives you useful information in predicting whether B occurs. But in independence, we require that it should not give you any information for predicting whether B occurs. So given that's the case, so we should know that mutually exclusive events should not be independent events. Okay, so I hope this makes sense. Um, I think given the time constraint being, we probably won't have enough time to go through the rest. And I hope you find today's lesson quite useful. And thank you for listening.